Good morning, everybody. So today we are going to begin Unit 8, which is about states of matter. You probably know from middle school that the three states of matter are solid, liquid, gas. Yes, plasma is in there too, but we are not going to look at that one. So for today, you need to download or print, if you have the capability, your Unit 8 notes. I will give you a packet on Wednesday when we have class. So I have emailed you guys the pages that you need to complete today's assignments, but you will get a full note packet, including these pages, on Wednesday. Your tasks for the day are to watch the 3 videos that are attached in this email and also linked on Miss Ward's YouTube page. The 3 videos we will cover today will talk about the properties of each of the states of matter. So the first video will look at the properties of gases, the second video will look at the property of liquids, and the third video will look at the properties of solids. So let's get started. This is video 1, so let's get started on gases, the properties of gases. So the first thing that we need to talk about is the kinetic molecular theory of gas. It has 5 parts. The first part is which says gases consist of large numbers of tiny particles that are far apart relative to their size. So in gases we have lots and lots of particles, but those particles are very, very, very small. So even though there are a lot of them, because they are very, very small, and based on the property they have as a gas, they're going to be far apart relative to their size. So for us, if we were looking at a sample, they might look close together, but relative to their size, they are very far apart. So the second part of the kinetic molecular theory says collisions between gas particles and between particles in the wall or whatever container they're in are elastic. And what elastic means is there's no net loss of kinetic energy. The kinetic energy is equal and opposite. So what that means is if 2 particles collide, if one's going really fast and one's going really slow, that doesn't mean that the fast one is always going to be moving fast. It just means that however fast it was going, if it transfers some of that moving energy or kinetic energy to the other particle, none of that speed will be lost from all the particles. So one might slow down and one might speed up, but the overall kinetic energy in the container will remain the same. So they won't all start to slow down and eventually slow down completely, and they won't all speed up exponentially as well. So 3, gas particles are in continuous, rapid, and random motion. So gas particles, they're continually moving around quickly, relatively, and their movement is very random. It has no method or uniformity to it. The fourth part says there are no forces of attraction between gas particles. So as they're moving past one another, they will not be attracted. They won't. One is not pulling the other towards itself. The fifth part says the temperature of a gas depends on the average kinetic energy of the particles of the gas. So temperature directly relates to energy. We talked about that in the last unit. And the specific type of energy that we were talking about is kinetic energy. And I like to think of kinetic energy as moving energy, the energy of its movement. So when you think kinetic energy, think the energy of how it's moving, fast, slow, and things like that. So if the temperature is high, the kinetic energy is going to be high. If the temperature is low, the kinetic energy is going to be low. So the higher the temperature, the quicker the particles are moving. Here's the equation for kinetic energy. Ke stands for kinetic energy, and it's 1/2 mass times velocity squared. So one of the things that we get from number 5 is that if 2 different types of gas molecules are at the same temperature, so say we have chlorine gas and hydrogen gas, and they're both in the same container at the same temperature, they will have the same kinetic energy, because temperature directly relates to kinetic energy. However, that doesn't necessarily mean they're moving at the same speed, because they might have different masses, and because they are different gases, they do have different masses. So the smaller one will move more quickly or have a higher velocity. I've kind of drawn it out in this equation. So if these two kinetic energies are equal, you can see kinetic energy 1 equals kinetic energy 2. But if you have a higher mass, the velocity must go down, and the lower mass, the velocity must go up. So the bigger mass will have a smaller velocity, and the smaller mass will have a bigger velocity in order to keep their kinetic energies equal. So again, just because two gas molecules are at the same temperature doesn't mean they are moving at the same speed. It only means they have the same kinetic energy. Now, if they are the same gas, they are moving at the same speed because their masses are the same, their kinetic energies are the same, their velocity has to be the same. So the next thing we're going to do is we are going to draw a figure first to represent the first 4 assumptions, and then we'll draw another one to represent the 5th. So you can see that box in your notes right below these 5 principles. You can use that box to draw out some of the things we're going to look at. So if you remember, the first thing says gases consist of a large number of tiny particles that are far apart relative to their size. This is going to be the drawing we're going to come up with, and you can see these are small relative to our box. I mean, we can only draw them so small, but they are far apart relative to their size. They're not very close together. The second part says collisions between these particles and the wall are elastic. There's no loss of kinetic energy. So the biggest way we represent that is with these collisions with the wall. And you can draw, this picture doesn't have any colliding with each other, but you can draw that. But you can see that this arrowhead, it's the same length before as it was after. It didn't lose any of its speed. The length of the arrow is meant to represent its speed. So the longer the arrow, the faster the speed. But you can see all of these arrows that collide with the wall, the before line is the same length as the after line. The third principle said gases are in continuous, rapid, and random motion. You can see that all of these are moving. Our length of our arrow says that and you can see them a little longer here, they're moving pretty rapidly, and their movement is random. None of them are moving in any specific orientation. The fourth one and the last one we're going to represent in this picture says that there are no forces of attraction between the gas molecules. Now, some people like to draw like an X that says there's no forces of attraction, but you can see any of these that are close together, like this one's a great example. These two are very close together. However, they are moving in completely, not perfectly opposite, so they're not repelling, but completely random and not towards each other. So they're not being attracted to one another. Another example I like to see is like these two right here. They're brushing past one another and in no way being attracted to one another. So here's another drawing that you can see. The thing I like about this one is you can see their speeds are different. You can see this one is moving faster than this one. But again, these arrowheads are roughly the same length before and after they collide. All right. The next thing we're going to do is talk about the 5th assumption, which talks about temperature and how it directly relates to kinetic energy. So you can see here, and I really like this diagram. You can put this one off to the right side of that box or just draw it separately. But you can see gases at low temperature have a low average kinetic energy. You can see their arrowheads are a lot smaller. Now this one is smaller than this one. It doesn't mean they're all going to be the same necessarily, but they are all relatively small. And then when you heat it up at a higher temperature, it's going to have a higher average kinetic energy. Again, that word average is very important. It doesn't mean, you can see this arrowhead over here is actually the same length as this arrowhead over here. It doesn't mean that two particles in the two containers can't have the same speed. It just means the average overall speed is a lot higher over here. All right? So pause the video, take a minute to draw those pictures if you would like. Hopefully they'll help you remember the kinetic molecular theory for gases, and we will continue to come back to that picture as we recall this theory later in the unit. But let's look at some of the properties of gases. Let's look at some of the properties of gases. So the first one we're going to talk about is expansion. Gases do not have a definite shape or volume. Gases will fill any container in which they are enclosed. So if we look here, Okay, this picture and this picture have the same amount of gas particles. No matter if we constrict the amount of space the gas particles have, or if we open it up, they will fill whatever container we give them. So that's what we call expansion. Fluidity. Theory assumption number 4 from our kinetic molecular theory states that there are no attractive forces between gas molecules. So gases flow as liquids do. Now the diagram I have here is specifically for a liquid, but you can just think of gases doing the same thing. So when you pour something out of like an Erlenmeyer flask like we have here, you can see gravity starts to take one of the particles. So because these two particles are not attracted to one another, even though they're right next to each other, there's no force of attraction. So when this opening happens, gravity will pull this particle down and it's able to flow. Okay, so the next molecule can move into the opening for the opening that was left by the previous particle that flowed out. So gravity has caused the molecule to fall out of the flask and flow like a fluid does. The next property we have for gases is that they have a very low density. The density of a gas at atmospheric pressure is much less, like 1/1000th of that of a liquid or solid. So it's very, very small. Gas particles are much more spread out than liquids and solids. So I've given you a picture of the three. We kind of looked at this one a little bit in the last unit, but you can see the gas particles are much more spread out than a liquid and significantly more spread out than a solid. So they are far apart relative to their size. They're going to be spread out, which causes a low density. Remember, density is mass per volume, and for this unit we can just think of it as particles per volume. So in a given amount of space, how many particles are you going to find there? If you find less, it's a lower density. The next thing we're going to talk about is compressibility. So to compress means to decrease the volume. So the volume of a gas can be decreased when an outside force pushes the molecules closest together. And because gases naturally take up the space they're given and they are very spread out, if we constrict that space, we can push them closer together because there's a lot of empty space available. So you can see we have this piston and it's compressing the gas particles into a smaller area. Because most of gas's general area naturally is empty space, and they're very spread out, we can compress them into a smaller amount of space. So gases are very, very compressible. The next property we're going to talk about is diffusion. So gases will readily mix and fill empty space to create equilibrium in the spacing of the gase's molecules. So a great example we have is this diagram or this GIF right here. So gases, as they escape, they will mix evenly to create equilibrium. And equilibrium means there will be an even number of one gas particle with another. So think of the blue ones as the air and the green being some gas that we're letting out into the air. Well, the gas is going to spread out so that the gas has spread itself equally so that we find the same ratio in any given area of the air. So you can see if we were to cut out a little box area of this section once the gas particles have been released, there's the green has spread out as much as it can to create an equilibrium. A great example of diffusion in real life is perfume. So when you spray perfume, it's really, really, really strong at first. But then as it spreads out throughout the room, it diffuses. So it creates an equilibrium so that instead of a really strong small area, there's a big area with a very light smell. It's also, and everyone likes to bring this one up, and Miss Ward said it was all brought up again this year in her class, but when you pass gas, it's very strong. So as the gas starts to spread out, people in the room start to smell it. However, they are smelling it at a lot less concentration. It has diffused throughout the room, and then you finally get the equilibrium. Eventually, the smell, it's not that it's really going away, it's just diffused so much that it doesn't, it's not picked up by our nose anymore. The next thing that we're going to talk about is effusion. Okay, gases can escape containers by passing through tiny, tiny openings. So the smaller or the less mass that the gas has, it will escape faster. So if you look at this container, you can see that the little green particles are escaping a lot faster than the blue ones. But one thing I want to be clear about when we talk about these tiny openings, in this GIF, this opening looks relatively big. But remember how small these gas particles are. So this hole is just as big as this blue gas particle. It has to be big enough that the actual gas particle can escape. But when we're talking about a hole, we're not talking about something that we would visibly be able to see as a whole. A great example we like to use is a balloon. And we're not talking about poking a hole in a balloon or the original opening in a balloon. We're talking about if you fill a balloon with helium and you tie it off and you put it in the air, it's going to float. But eventually, as time and days pass, that helium will escape. The balloon will actually slightly decrease in size and it will start to not float anymore. And that is because the helium gas is escaping through tiny, 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 almost like pores in the balloon's casing or the balloon film. So that helium is actually escaping to and then it diffuses throughout the room. Also, air is actually entering into the balloon, which doesn't cause a balloon to float. So that's why the helium doesn't completely escape and the balloon never really completely deflates, because helium is escaping and air is entering. So fusion can happen in both directions. The helium doesn't just escape, air also enters the balloon, again trying to reach equilibrium. Both diffusion and diffusion work towards finding equilibrium. So please remember both of those are working to create equilibrium. The next thing we're going to talk about is an ideal gas versus a real gas. So real gases, so the gases we deal with in real life, do not follow all of the 5 kinetic molecular theory assumptions all of the time. Real gases have a volume. They have attraction a slight bit. If you remember when we talked about gases, which are going to be our covalent bonds, even nonpolar have London dispersion. So every type of gas is going to have some force of attraction and a variety of speed. So they're not all going exactly at the same speed if they're at the same temperature. So noble gases and nonpolar gases behave the most like ideal gases. That's because these are the ones that only have London dispersion forces, so they have the least amount of attraction, which causes the other things to fall in line the most with the kinetic molecular theory as well. Polar gases, such as ammonia and H2O or water, do not follow the ideal behavior in many circumstances due to their polarity, and sometimes both of these, for example, also have hydrogen bonds. So they have a lot of forces of attraction, and they aren't going to behave as much into the kinetic molecular theory as we would like. The ideal gas law, which we will, you might have heard before, we call it PIVNERT, given this acronym. This is the equation. We will look at this more in the next unit, but it does still provide a good explanation of the behavior of real gases, even though they don't behave as ideally as we assume they do in the kinetic molecular theory. So again, no gases behave like the ideal gases, which ideal gases are gases that follow the 5 points of the kinetic molecular theory. All gases are real gases and don't follow that, but some are close. Noble gases and nonpolar are closer to ideal than polar, but the ideal gas law, which assumes that they follow those 5 points, does still give us a good idea. So that's all we have for gases. That's the end of this video. If you will move on to videos 2 and 3 on liquids and solids.